Hello and welcome to the first lecture in the 8400 class for the hybrid component. This topic will be around software engineering basics. It's based off of chapter 1 in your book. So without any further ado, I will begin. All right, so the first thing we're going to want to talk about, if we're going to talk about software project management, is going to be what is software. It's important to understand what software is, as well as what software engineering and development is, if we're going to be managing projects involving them. So software, in a very limited definition here, is three components, which are instructions, data structures, and documentation. A lot of you have hopefully been working with software already, so you know a lot of these concepts, but instructions are basically going to be all the features, functions, and performance of our computer programs, the code that we write that's executed. Data structures are the actual abstract structures that are created that allow us to manipulate data and information that is necessary for us to run our programs. And finally, we want to have documentation, because if we don't have a way of documenting exactly how our program runs, the next person who is going to be modifying it or updating it is going to have a harder time. So let's talk a little more about software development. Software development is a complex process, involves creation, testing, maintenance of computer programs. So you got physical products, which are usually manufactured in a factory. Software is actually developed outside of a factory by a team of software developers, usually through a series of steps that require careful planning and attention to detail. And that's really the core of software, our software engineering series here, is that we want to identify what these steps are and make sure that we understand them. Well, one big difference between software and physical products is that software doesn't wear out in the same way physical products do. It can deteriorate over time because of changes in the operating environment, technological advances, new security threats, or somebody who decides they want to create a cool new feature that breaks the system, right? So we'll learn more about feature bloat eventually and how that can affect the deterioration of software. While the software industry is moving towards more of a component-based construction, pre-built modules can be combined and create custom applications. Most software is still custom built. That means that this requires a lot of resources for our software development projects and expertise to complete them successfully. All right, so what sort of domains exist for software applications? Well, healthcare, for example, requires software that can securely store and manage patient records, assist with diagnostics, provide personalized treatment plans. On the other side, you have finance, which software is used for trading, risk management, fraud detection. In education here, we use software to help you all as students learn in new ways. Interactive digital textbooks like Zybooks or gamified learning platforms. I mean, Canvas is a learning platform. I'm not sure I'd call it gamified, but definitely feel like that would be a bonus to add to it. And then we have software for entertainment, video games, virtual reality experiences, streaming platforms. Software is used in so many different places. Manufacturing relies on software to handle its complex supply chains, optimize production processes, and ensure quality control. Transportation, logistics, route optimization, autonomous vehicle technology, such as self-driving cars. Communication software with your messaging apps, video conferencing tools like Zoom, email clients, social media platforms using software on a global scale, and e-commerce. Software that uses to manage online stores, process payments, track inventory. All of these different things indicate that software is really pivotal, the foundation of our society and culture today, and the way that it operates cannot be overstated. So if you take a look at this chart, you can see that the expectation, or the idealized curve, I'm not going to say the expectation, the idealized curve of wear versus deterioration, you can see is very flat. So over time, and the idealized curve says the failure rate will consistently stay low from being high in the beginning. Unfortunately, that's not the way it actually works, because there's some sort of changes that are happening within the software. You can see it causes these failure rates to spike. All right, so let's talk a little bit about legacy software. So legacy software is any software that has already been established and perhaps it's falling behind on times. It's not really using the technology that is required in order to maintain competitiveness with any sort of corporate competition, or keep in line with the scientific processes of evolutions that we've made, or what the consumer wants. So let's talk about each one of these. We've got adaptation, which is going to be what we want to do to modify the software code and configurations, or the dependencies, align them to requirements for any sort of new computing environment. For an example, any software that's developed on traditional desktop environments may need adaptation to be run on mobile devices or cloud-based platforms. Enhancement involves adding new features, improving functionality, modifying existing components that align with changing business needs. So this usually begins with the process of gathering and analyzing new requirements from stakeholders, which is what we're going to be doing in this class. Enhancements also may include integrating new workflows, supporting additional data formats, incorporating advanced analytics capabilities, so on and so forth. All right. So the next one is an extension. So interoperability is crucial for seamless collaboration between different software systems and databases. So a software extension involves implementing interfaces, protocols, connections that enable communication and data exchange. This may include developing APIs, using standardized data formats, or implementing middleware software to facilitate integration. Oftentimes, middleware software solutions allow us to take one application or software and another application and have them coordinate or collaborate in a way that they were not able to before. Re-architecturing is going to be the next legacy software action that we're going to talk about. So this involves restructuring the components, our communication mechanisms for the support network, security, or scalability. We're going to talk a lot about this in re-engineering when we get into our software maintenance and evolution later. This could mean adopting a client-server architecture, implementing service-oriented or microservice architectures, or we could be incorporating cloud computing concepts, which is a really big deal these days because a lot of different softwares that are hosted on-prem are instead moving into a cloud environment in order to, for a lot of reasons, saving costs, security, simplicity of running it or having it hosted somewhere else. Re-architecturing is also going to consider factors like data synchronization, load balancing, fault tolerance, and data security. So all these are different aspects that have to be done with a piece of software that's become legacy and needs to be brought up to date so that it can operate and be effective in the modern technological environment. So IEEE's definition of software engineering, you can see here, states, I'm trying to read slides as little as possible, but I am going to read this definition. The application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. That is, the application of engineering to software. So I want to just take a moment here and talk a little bit about what the difference between software engineering and software development is. So software engineering is going to deal with the entire system. It's going to deal with operations, it's going to deal with testing, it's going to deal with the DevOps, it's going to be dealing with all the different different aspects of the tech environment and the people in it in order to ensure that the system runs smoothly, the software from inception all the way until production and beyond is effective. A software developer, and software development's a little bit different. It's going to be basically the person who is working on developing the code base as well as modifying it. Software developers also will be performing maintenance tasks, fixing bugs, adding features, but they're not going to be really concerned with how the system itself interoperates, right? So it's not going to be, they're not going to be concerned with that. They're going to be given instructions from the software engineers. That's not to say that they're under them or less than them. It just means that they have a different function. They're more hands-on and practical. All right. So let's talk about some software engineering layers. We got tools, methods, processes, and a quality focus. So let's talk about each one of these. The tools layer in software engineering is going to be our technology, software applications, IDEs, utilities used by software engineers and developers. So some of these are going to be your IDEs, your code editors, version control systems, testing frameworks, project management tools, documentation tools. So we'll be taking a look at a lot of those in this class, especially looking at Jira as well as Confluence. So those are two examples. So the methods layer is going to encompass principles, techniques, and practices employed to guide the software development process. So you're going to be using these to analyze, design, implement, test, and maintain our software systems. Some examples of these, but definitely not limited to these, are our waterfall model, agile methodologies, object-oriented analysis and design, the design patterns, and test-driven development. Our process layer is going to be our overall framework and set of activities that govern the life cycle of software development. It includes the defined processes, workflows, and methodologies followed within an organization or project. So this is going to be usually your requirements engineering, which we will be going over, testing and quality assurance, which we'll touch on, and deployment and maintenance, which we'll also touch on. Finally, I've got our quality focus layer. I can't emphasize enough the importance of your software being high quality, right? You wouldn't want to deliver a product to a customer that's going to fall apart in a year, although I will say there's probably companies out there that intentionally design products that fall apart in a year, which I've experienced. And some sort of skewed business ideology that if they do that, then the person will go buy a replacement within a year. Sadly, it actually works. But we're not going to be those people. We want to produce quality products for our customers. That means that we're going to have quality software. We're going to meet user expectations and requirements. We're going to incorporate quality-oriented practices throughout the software development process. This is going to involve software testing, code reviews, continuous integration, continuous delivery, and performance optimization. Okay. So let's talk a little bit about some of these process framework activities. I'm not going to go too deeply into these, but basically start with communication. You want to communicate with your team, you want to communicate with your stakeholders, and you want to understand what is the goals we're trying to achieve. What are the goals we're trying to achieve? And then you're going to involve planning, estimating resources, creating schedules, setting milestones, doing all the things in order to ensure that everyone has a clear idea of how the project's going to move forward. Then we move into modeling, figuring out what our requirements are, analyzing them, and then, of course, design of the actual software. Construction, where we do the code generation and testing, and then deployment, which is delivered to the customer. So I want to be very clear about this. These are put in an order that makes sense. They feel sequential, right? And yes, most of the time they are handled sequentially. But as we'll learn next week in our agile development, we don't want to be beholden only to this sequential development. We want to be able to be iterating through these sequentially and also being able to move back and forth in between them. That is most important in order for us to have a model where we're capable of handling changes on the regular. In this class, we're going to be doing our sequential processing, at least for our topics, is going to be communication, modeling, planning, construction. Well, we're not going to actually be implementing, and then deployment will be delivery at the end to, of course, me as the professor. But we're not only going to follow that model, we're going to be jumping around as well, back and forth, back and forth. Of course, communication happening constantly. Requirements engineering, which is the modeling, we're going to be doing that, and then we're going to be coming back and doing it again, right? Because we're going to be modifying. Planning is going to be done, and we're going to need to modify that based on what our customer wants. We'll talk about testing and then deployment. All right, so umbrella activities that exist for software engineering. We want to have software project tracking control, which allows us to assess progress against the project plan, take any necessary action to maintain the schedule. Risk management we'll talk about in this class. We're going to assess what risks may affect the outcome of the project or the quality. Software quality assurance, or SQA, is defining the conducts and activities required to ensure software quality. So in our series, this quarter, we're actually going to be discussing software quality assurance and software testing to a very minimal degree, and we're going to dive a lot deeper into that next quarter. Technical reviews, assessing software engineering work products. This is like our code reviews. Measurement, we want to have defined measurements for process, project, and product that is going to help us understand what the stakeholders' needs are, as well as all of the other framework activities needs. And we'll have some measurements that we're going to take a look at in this class. And then we'll be introducing more measurements in the next class. Software configuration management is something we're going to do in here as well, managing the effects of change throughout the software process. This is also going to be where our version control comes into play. Reusability management defines the criteria for the product reuse, establishes mechanisms to achieve reusable components. Something we'll dive into deeper next quarter, but is important to keep mentioning here is the idea of modularity. We want less coupling and more cohesion. So we want to be able to be reusing modules and parts of our product and our code. And we've learned a lot about this with object-oriented programming before. And then work product preparation and production is going to be the activities required to create work products such as models, documents, logs, forms, lists. And you'll be defining some of those with your teams. Okay, so I'm not going to read through each one of these. This is basically a list of all the differences that could exist between one process and another. And the idea is that not all software processes are going to be the same. Not all of them are going to require the same amount of detail in certain aspects or others. Some examples could be, so actions and tasks could be defined into more detail in different framework activities. Quality assurance may be more strict. There may be different project tracking control activities, or how much autonomy the software team is getting. So feel free to take a look at that. It just gives you an idea. And the big takeaway here is that we need to know that not one size shoe fits all when it comes to this development, software engineering and development. All right, so using Polya's method, here's a simple and powerful way of solving problems. So software engineering ends up being a problem. We want to do a project to solve a problem. We want to understand what the problem is. We get that communication analysis done, so communication requirements analysis. Plan a solution, modeling, software design, carry it out, right? And then we're going to generate the code, and then examine and ensure that it is quality, and test it until we can't stay awake anymore and we are completely exhausted. You know, for me, I definitely remember one of my more memorable moments in software engineering when I was in industry was staying at work from 9 a.m. till 11 p.m. testing until I was nearly like falling out of my chair. And so when you get started in the industry, one of the things you're going to find is that you're going to be, you're going to mentor, you're going to people over you, you're going to be an intern or, a dev one or whatever, and you're going to basically be beholden to when they say it's time to stop testing, if you're involved in the testing process. And any good software developer or engineer should be involved in some of the level of testing process. So at least that's my opinion. All right, we're going to talk through each one of these real quick, just present some questions. Who has a stake in the solution of the problem? Who are the stakeholders? What are our unknowns? We want to know, what don't we know? What do we know? Can the problem be compartmentalized? Can we turn it into smaller problems in order to understand it better? Can it be represented graphically? Let me just tell you, I can't understate or overstate the importance of having some sort of graphic to understand things. It's very helpful. We want to plan a solution. Have we seen other problems before? Can we use historical data or methods that we used before to help us fix the problem? One of the things we're going to take a look at in this class is using historical data for estimation. Has a similar problem been solved before? Can subproblems be defined, breaking up into subproblems so we can understand it? Can you represent a solution in a manner that leads to an effective implementation? Right? So this is all about modeling, creating a design model, which we'll get into more next quarter, but it's important to understand that concept now. Does our solution conform to our plan? So we want to be aware that as we're implementing or we're developing, that our plan is being followed. Is each component part of the solution provably correct? So this is interesting. So a lot of times, at least in what I found in industry, you'll have this software that's created, and then you have the solution, which we're like, okay, we want to create this app, and in this app, one of our functional requirements will be that the user can actually log manually how many times, how many reps, and how their workout went. If we find in our app that we're able to do that, and it's logged into a database, and we can access it and look at it later, sure, that looks like success. But we need to have some sort of correctness proof to ensure that whatever's been trying to be done has been done. We need to have the code reviewed. We need to have some sort of quantifiable evidence that this is true. And you're going to find that there's going to be a lot when you go out there in the workforce, you're going to find that isn't always the case. And a lot of times it's more about if it seems to work and our testing environment says it works, good, and they're not using a correctness proof themselves, then we usually be like, okay, we're done. And that's fine. It's all about what you're going to find is that when you go out there, you're going to find that it's all about the level of detail that your company wants you to go to. You can make things better. I suggest you implement changes slowly, especially when you're new, or hesitantly. Diplomatically is another word I'm looking for, because you're definitely going to have more impact on making changes to processes when you have more experience. But in the beginning, you're going to find, you're going to be learning, as well as your voice will probably not be heard as much. I could be wrong. Every situation is different. And I guess that was the whole point. So lastly, we want to examine the result. Is it possible to test each component as part of the solution? And does the solution produce results that conform to what we were looking for? Right, so we want to validate against all of our stakeholders' requirements. All right, so this guy here, his name is David Hooker, and he came up with some general principles that we want to keep in mind when it comes to software engineering. The first is the reason it all exists. So at the core of software development is the goal of creating products that provide value to users. So understanding the needs and requirements of the end users is absolutely crucial. Whether it's a small utility or a large application, always keep the user's perspective in mind. Building software that doesn't add value or solve real problems is just wasted effort and resources. Next, we have this acronym KISS, Keep It Simple Stupid. This is all about design. We want simplicity. So simplicity is a virtue in software development. We strive to keep the design and implementation as simple as possible. Avoid unnecessary complexity and over-engineering. Often these are easier to understand, maintain, and troubleshoot, and the people who are doing that will thank you. Maintain the vision. So clear vision is absolutely essential. Having a clear vision of what the software is intended to achieve is crucial for our successful development. We want to have like this guiding light through the project's life cycle, helping the team stay focused on their goals, avoid straying off course. This also aids in decision making and prioritization. Keep in mind, what you produce, others will consume. In a collaborative world of software development, code and products are often consumed by other developers, teams, or even external users. So we always want to write code and build software with the understanding that others will have to work with it in the future. Maintain clean code, proper documentation, consistent practices to facilitate collaboration is going to make the people that are going to be working with your code in the future a lot happier. Be open to the future. Don't design yourself in a corner. So these projects need to be flexible and adaptable. Design decisions should consider future changes and expansion. I cannot emphasize that enough. We're not going to get too deeply into design, but we will next quarter. And you want to make sure that when you're designing, you have in mind, okay, what I'm designing is probably going to change at some point. How can I facilitate and design this in a way that makes that easier, so they don't have to rewrite everything? Don't have rigid solutions that become barriers to incorporating new features and adapting or evolving requirements. Be open to change. It's going to happen. Change is going to happen. You're going to put that software out, and like days later, you're going to have a bug. You're going to have something you have to change. It's just the way it is. Plan ahead for reuse. Reusable components and code are valuable assets. Whenever design and build with reusability in mind, it's probably one of the most essential things when you're developing. Reusing existing code not only saves time and effort, but also improves consistency and reduces the likelihood of bugs in the future. Building for reuse promotes efficiency and maintains a consistent user experience. Finally, think. Placing thought before action produces results. So critical thinking is absolutely essential for effective problem solving and decision making. Before diving into code or implementing a solution, take the time to think about the problem, potential approaches, and implementations of each decision. Implications. Thoughtful planning leads to better solutions. So this field that we're in is not a no-brainer. We don't get to go into work and be like, okay, I'm just going to cruise through work today, not really think about it, just go on automatic. Now, that's not the way that our job is. This field requires a continuous amount of critical thinking and awareness of what we're doing and how we can change and improve and grow. That's why we're getting paid good money. Also because our product is very useful. So that is the end of this particular lecture. So thank you, and I'll see you in the next one.